Okay, welcome to another episode. Today's learning objective is to introduce ideas of mutually exclusive events and independent events, and then we'll kind of talk about some probability rules that come with those. So let's talk about an example that we've already discussed a few times. Say we've got a coin, right? Such as this, and then we flip it. And when we flip it, we can get a heads or a tails, right? There's two possible outcomes. And we also know that they're kind of equally likely. So we say, for example, probability of heads is equal to, well, the conditions which satisfy on the top is the conditions that satisfy a constraint, i.e. there's only one time, there's only one face of the coin that's heads, so that's one, and there's two faces in total, and it's equally likely to land on either face. So a probability of heads is a half. And if I was to ask you the probability of tails, you'd say kind of a half as well. But what happens if I ask you, say, what's the probability of for it to land and there to be heads and tails? Heads and tails. There's no constraint which satisfies this, right? You can't get a heads and a tail at the same time. You can get either or. So the probability of heads and tail is 0 over 2, which is just 0. And this is what we call mutually exclusive events. There are events that can't happen at the same time. So, for example, another example might be, if we roll a dice, if we say the probability of getting 1 and 2, well, we can't get both those together, right? They can't happen in the same. A dice can only show one number, so the probability of that is 0 again. So mutually exclusive events are basically events which cannot happen together. If one happens, by necessity the other cannot happen. So, for example, another example might be, say if it's raining, you're seeing the probability it rains at the current moment. It can't be, for example, raining and not raining at the same time. Those are mutually exclusive. And we have some interesting properties because of this. So if we have mutually exclusive events, right, the probability of, say events A and B are mutually exclusive. I'm just going to write ME. That's not really a used notation, but I'm just to save a bit of time. Are mutually exclusive. So probability of A or B is equal to probability of A plus probability of B. That's how we calculate the probability of two events happening, PA or P, probability of event A occurring or B occurring is the equivalent to saying probability of A occurring and probability of B occurring, because they're mutually exclusive. Now let's think about let's say there's only two events that can occur. Say, for example, here we have the example here, heads. We can either have heads or tails. When we add up P heads plus P tails, so probability heads or tails, we have P heads plus P tails, right, from this, which is a half plus a half, which is equal to 1. And this is kind of an interesting thing that we get from probability, that if we have, say, certain number of events which are all mutually exclusive, if we add up all the properties together, they're going to sum to 1. So, if we have mutually exclusive events, the probability, their probabilities sum to 1. And let's think about why this is the case, right? So let's think about, in general, what's the probability, when we have, say, a sample space with, say, a certain number of outcomes. If we think about what's the probability of saying the outcome A, B, C, and D, and all those outcomes happening, the probability it's one of those is going to equal to 1, right? So, for example, if we have a dice, right, such as this, if we have, say, the probability of it being a 1 or 2 or 3, or 4 or 5 or 6, that's going to equal 1, because this is the whole sample space. These are all the outcomes I've said, and the probability each of those equaling kind of happening, that has to be 1 kind of by definition. And if we have mutually exclusive events as well, right, then we have that P1 or P2, etc. will equal to P1 plus P2 plus P3, etc. So that's why when we add up all the probabilities for mutually exclusive events, that will sum to 1. And this is a useful property we need to use sometimes. So look at this question here, for example. Let me zoom in real quick. So there are only red counters, blue counters, white counters, and black counters in the bag. The table shows the probability that counter taken at random from the bag will be red or blue. So the first thing I see when I think about this question is, right, you say that you see that one counter is taken from the bag, and the probability, say it's a red counter, or say the event that it's a red counter, has to be mutually exclusive from, say it's a blue or a white or a black, because the counter can't be red or white and white at the same time. So these events are all mutually exclusive, and as such, when we add up all these probabilities together, that will sum to 1. So the number of white counters in the bag is the same number as black counters in the bag. And kind of if we have the same numbers of each counters, right, we can estimate that the probability will be the same. Well, we can tell that because, say, kind of if the numbers of those two are equal, the likelihood that we'll pick one as opposed to another is going to be equal. So, for example, like with heads or tails, or you say a dice even, say the probability of picking an even number is the same as picking an odd number, because there's the same number of even kind of faces as odd faces, for example. So work out the probability that Tanya takes a white counter. So we know two things. We know all these sum to 1, and we know that this probability is equal to this probability. So first thing we'll do for A, we'll say something like, remember how we always approach questions where there's unknown? We say A, kind of let the unknown thing be X, for example. So in this case, I'll say, let me move down here actually, A, in fact, we can just say, let's say P probability white equal X, and we know P white equals P white is equal to P black, which is equal to X from that first thing. And no, sorry, not from the first thing, we know from this thing, the number of white counters is the same as the number of black counters, and we know that this sums to 1, and we know 0.2 plus 0.5 plus x is equal to 1. So 0.7 plus 2x is equal to 1, 2x is equal to 0.3, and then x is equal to 0.15. And then, we'd say then the probability is 0.15. There are 240 counters in the bag. Work out the number of red counters in the bag. We'll actually talk about this in a later video. I shouldn't have included this part question. Let's move on to the other question I have saved up. This is actually an easier question. So actually pause the video for a second and give this question a go. Okay, so hopefully you've given the question a go. If you haven't, I'm going to give you another chance to give the question a go. I'll actually wait again. Okay, have you done it? I feel like you haven't done it, so third time's a charm, so go ahead and actually do it this time. Okay, cool, you've probably done it now, hopefully. 4 teams, City, Rovers, Town, and United play a competition to win the cup. Only one team can win the cup. So only one team can win the cup. That's literally kind of the real world way of saying the events are mutually exclusive. Because, as it says, only one team can win the World Cup, so the probability, say, City wins is obviously going to be mutually exclusive from, not the probability, I mean the event City wins is going to be mutually exclusive from, say, Rover wins or etc. And so from this straight away, we know those probabilities will sum to 1. So, we know 0.38 plus 0.27 plus 0.15 plus x equals 1. Now rearrange, so let's collect the things on the left. 0.38 plus 0.27 plus 0.15. Let's see if my mental math is good enough. So 38 plus 15 is 40 plus 13, which is 53. 53 plus 27 is 60 plus 20. So 0.8 plus x is equal to 1. X is equal to 0.2. And now since we're all, usually allowed a calculator, I check this anyways because I don't often trust my mental math. So, yep, that was correct. And so that's how you do a question like this. So this is a quick recap about what mutually exclusive events are. Mutually exclusive events are basically when the events cannot happen at the same time. So and because of the fact that events cannot happen at the same time, we have that the probability A or probability of B is equal to PA plus B. That's kind of the consequence of mutually exclusive events. I'll kind of when we talk about Venn diagrams in a few video, I'll kind of show more of an intuitive reason for why mutually exclusive means this kind of thing right here. But just for now, just remember this in your head. Mutually exclusive means this. This is the probability rule you get for mutually exclusive. Or we can say, for example, and this is what it means, and it also means this: P, A, and B is equal to 0. And kind of these are very much the same thing, and I'll show you why kind of in the later video. And since we know that the probability of, over the whole subset, right? So the probability of, for any probabilities, right? The probability of all the events, A or B or C or D or E, etc. For even if it's not mutually exclusive events, all the events, if you can consider them, the probabilities of, A or B, etc. will sum to 1. But in this mutually exclusive case, we have the special case that when we have ORs, we can just get rid of the OR sign and have a plus sign like this. And because of that, for mutually exclusive events, we have the probabilities of each event will sum to 1. This isn't the case for kind of non-mutually exclusive events. So for all probabilities, we have P, A, or B, or C, etc. will sum to 1. But for all probabilities, the following, that PA plus PB plus PC, etc., that does not have to equal 1 for all probabilities. This is only true that PA plus PB plus PC, sorry for the poor handwriting, etc., will equal 1 for mutually exclusive events. So this is a key thing to remember. So for normal probabilities, this does not imply this. Because of this, we don't have this, but for mutually exclusive, we do. So just really important thing to remember. Let's talk about something called independent as well, independent events. And independent events, kind of almost from the name, you can kind of guess, is that the probability of one thing happening or one event happening is independent of another event happening. So for example, me kind of tossing a coin and rolling a die. So, me getting a heads on the toss of a coin and rolling a 3, for example, those are independent events because the toss of the coin doesn't affect the 3 somehow. But say, say the event of me having an umbrella and it raining, those are dependent because if it's raining, I'm far more likely to have an umbrella on me than say if it wasn't raining. So those are dependent events. So you have two things: independent events and dependent. And you just have to think about, does event A happening change the chances of event B happening? If the answer is no, then it's independent. If it's yes, then it's dependent. So let me just give you a few examples, and that's just so we can kind of see if you've got the definition nails down. So if we had, say, toss a coin 3 times, the probability we get, for example, getting a heads on the first toss and tails on the second toss, is that dependent or independent? So that's independent because the first toss doesn't affect what you're going to get on the second toss. And same thing if we were to say roll a dice multiple times. Say getting a 6 on the first dice and getting a 5 on the second dice. Those events are mutually exclusive because the probability I get a 6 on the first dice, me rolling the dice the first time round doesn't somehow have an impact on me rolling the dice another time round. But let's say, for example, say failing my driving test. So kind of saying, what's the probability of me failing my driving test the first time round, and the event I fail my driving test the first time round, and event I fail my driving test the second time round. Those are dependent because, for example, I have to fail my first test in order to take a second test, or I have to if we think about it in another way, saying I might improve, for example. So those kind of are dependent. So that's kind of the logic you have to think through. A lot of the time it will be quite obvious whether it's independent or dependent. Stuff like rolling stuff and kind of tossing coins, or like picking stuff out of a bag, that tends to be independent. But for example, if we have something like picking if you have a bag, right, and full of counters, for example, and you pick a counter out, and say it's red, white, and blue counters. So let's say there's 3 red, 3 blue, and 3 white. And so if we have saying that if I'm considering the event, I pick it 1 out. And then I kind of put it on the side. I don't put it back in. I just, I take the counter out. And I throw it away or whatever. So, instead of in the next time around, I only have 8 in the bag. So the probability in the first one I pick out is, say red, and the event that the second one I pick out is, say, red again. Those are dependent, because, for example, if in the first one, if I pick out a red, there's fewer reds. Now there's only 2 reds, 3 blue, and 2 white. So kind of these events are not independent, for example. So this is kind of something that might trip you up, in the sense that with replacement, i.e. you take a counter out and then you put it back in. Those events are independent now. But kind of without replacements, i.e. you take it out and you kind of throw away, as is in this case, that is dependent. So that's something we have to watch out for. And we have an interesting rule because of independent. So if independent, if events A and B, and kind of if I've been using events this whole time as kind of what really means event is just kind of an outcome or something happening. So the event that it rains, or event that the coin, it shows a heads, or the dice shows a 6. If event A and B are independent, then PA, so probability of A and B, is equal to PA times by PB. And this is kind of a crucial thing, so and this is another probability rule that comes up a lot. So let's say, for example, okay, we have a coin, and we toss it once. The probability the first time around we get heads. So first toss is heads, and the probability so we're looking for the probability that the first toss is a heads, and the second toss is tails. Okay, because if we think about this, the first toss and the second toss are independent. So if we get our heads on the first toss, that doesn't somehow change the probability or kind of change the likelihood of getting a tails in the second toss. So those are independent. So we know this is the probability of heads on first times by tails the second, and the probability of getting heads on the first toss is a half, as we've seen before, and the probability of getting tails on the second toss is a half. So that's just a quarter. Say if we have another one, say we have a dice, for example. Okay, and let's say the probability of getting a 6 first time round, so I'll just write 6, and then getting a 4, and then getting a 5. So the first roll we get 6, the second roll we get 4, and the third roll we get 5. Again, we know that these rolls are independent, so the probability of this is just if we multiply the probability of 6 times the probability of 4 times the probability of 5. So probability of 6 is just 6, as we know. Probability of getting 4 is also 6th, and same as getting the probability of a 5th is also 6th, which is 1 over 216. Another perhaps a bit harder one we might want to consider is, say, if we toss 3 coins, or toss a coin 3 times even, what's the probability of getting, P of getting exactly 2 heads? So we toss the coin once, toss the coin twice, and toss the coin 3 times. And then we get, maybe heads, tails, or heads, for example. And we can get loads of those different combinations, right? Our question is, what's the probability of getting us exactly 2 heads? So with this question, there's kind of 2 ways of approaching it. One is a kind of systematic listing strategy, where we say what are all the outcomes and which outcomes satisfy our kind of thing. So for example, let's list all the outcomes. We can say we can get, for example, tails, tails, tails. We can get tails, so tails on the first one, tails on the second one, tails on the third one. We can get tails on the first one, tails on the second one, heads on the last one. We could get tails, heads, 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 tail, heads. So the way I'm doing this is kind of, I'm changing this to heads, heads, and then we should kind of probably have say a heads, heads, head. And now I'm going to go kind of changing the last one to tails. So H, H, T, H, T, T. And then again, the last one is T, T, T. And then I think, missed one out as well. We have something like tail, heads, tail. And we have heads, tail, heads. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you kind of have to check for duplicates. So let's see if there's any duplicates. I don't think there's any duplicates here. And the other way to do questions like these with heads and tails, if you have something like tails, 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 right? And then we went to tails, tails, heads, and then we have tail, heads, heads. And then we can also have the tail, heads, tail, right? And now we can think of kind of every time we see a T, if we replace that with a H, that should, I think, cover everything. H, 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 T then, so then H, T, T, and H, T, H. So that's 8. So there was 9 here. Oh no, sorry, there's just 8 here. So yeah, that's the other way we can think of doing this. And now we can think about how many of these are kind of exactly 2 heads. So let's change color for that. Okay, this has 3, this is 1. Okay, so this is exactly 2 heads. It's 1. This is another one. This is another one. So there's 1, 2, 3, and there's 8 in total. So the probability of that is 3 over 8. Or perhaps the other way we could do this, for example, is is a bit harder. So what we do is, for example, we can kind of look at this, right, and then we can say, instead of kind of adding all these up and dividing by it, we can think about, okay, so how many ways, when we think of exactly 2 heads, we can just go straight to thinking of these 3. If we can immediately think of these 3, right, we can think, okay, we can get either tails, heads, 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 tail, or heads, tails, heads. So the probability of exactly 2 heads is equal to the probability we either get, P heads, heads, tails. And here, if we see, we're actually, so the probability we get 2 heads is the probability we either get H, H, T, or T, H, H, or H, T, H. And we know these are mutually exclusive, right? So we can just say P, H, H, T, plus P, T, H, H. Because if you think about this as one whole event, you can't get, heads, heads, tails, and somehow get at the same time tail, heads, heads. That doesn't make any sense. So we know these are mutually exclusive, so we can just add them up. And we also know that kind of, with each, we know, so the probability of getting heads, heads, then tail is independent. So we can say, the probability of getting a heads, heads, then the tail is probability of heads times by probability of heads times by probability of tails, and then kind of the same repeated here. And this is going to be a half times a half times a half, which is an eighth, which is the same thing with this and this, because probability of head and probability of tails is the same. So that's an eighth plus an eighth plus an eighth, and there we go, 3 over 8. So this question here, we can use a systematic listing strategies, which might be a bit easier in this case because there's not too many options, and so kind of this might be a bit easier. Or kind of if we can immediately somehow think of the ways of getting a heads and the tail, and kind of getting 2 heads, which exactly like this, which this is actually a bit easier to list, isn't it? To think of heads, heads, tails, tail, heads, heads, and heads, tails, heads. I mean, this is a lot easier to list than kind of all the possible outcomes, for example. And then we use the fact that they're mutually exclusive to get this step here. I'm just going to write ME. So mutually exclusive. And from this step to this step, we know that they're independent. So we use both the facts that I've talked about, independent and mutually exclusive, in order to solve this question here. So as a kind of a quick recap before I end the lesson, mutually exclusive events, it means that probability of A or B or C, etc., is equal to PA plus PB, PA plus PB plus PC, etc. kind of, and when I say A, this is event A, probability of event A, probability of event B, or probability of, so probability of, event A or B or C is equal to the probability of event A plus probability of event B plus probability of event C. And, if we do this for all the events, this will sum to 1, because kind of this thing on the left will always sum to 1 for all probabilities, but this step here, from this to this, needs a mutually exclusive. And the other thing, we have independent, that PA and B is equal to PA times by PB. So these are the kind of the rules you need to remember. I'll talk about kind of the way to generally add this to say kind of in the other lesson, but just kind of remember these rules. We'll go over them again in another lesson, but it's kind of important to remember these rules for questions that I've kind of talked about. So hopefully that all made sense, and I'll see you guys in the next video.